Jean-Pierre Leburton is the Gregory Stillman Professor Emeritus of Electrical and Computer Engineering at the University of Illinois. His research focuses on electronic and optical properties of quantum structures, and over the past 25 years, he has also focused on bio-nano electronics. Jean-Pierre, thank you so much for taking the time today.
Thank you for inviting me.
So to start, could you tell the audience about your research on electronic and optical properties of quantum structures?
Yes, so actually after my PhD in Belgium at the University of Liège, there was an article that I read in a French review, which is called La Recherche, which it means in English is research, which is mostly the equivalent of Scientific America, where they mention actually the manufacturing or the fabrication of layer structure of semiconductor, very thin layer of semiconductor. So layers of semiconductor that are separated by a few nanometers. Nanometers is 1/1000th of a meter. And so this intrigued me because this was the opportunity, in fact, to tailor the electronic and properties of material with this kind of a technique, which is called, the first structure were in fact called superlattices. And so I got interested in this because this was an idea. Before that, my PhD was focusing on the transport properties of in semiconductors. I realized that in fact we can tailor this electronic property for different kind of functionality that we would need. So I was interested in this, and this is one of the reasons why I joined the University of Illinois after spending 2 years with device modeling with Siemens Research Lab. And I started my research on this kind of structure. So what are quantum structure? These are actually structures that are characterized by extremely small dimension so that the quantum properties of matter emerge. You know that for example, at the microscopic level, the electron has a dual nature. It is considered as a particle, but also as a wave. And the quantum structure gives the opportunity to, in fact, see and use the wave nature of the electron. And so this actually opened the field to a large number of applications. So the first kind of structure they were that were fabricated, investigated was what we call quantum well. This is actually layers of material where the particle like electron are confined along one direction, quantum confined along one direction, so that they exhibit a quantum mode, and are free to move in the two other directions of space. Later on, people actually were able to fabricate quantum wire where the quantum confinement is in fact achieved in a second direction. So now the particle is only capable to move in one direction from this name of wire. And finally, years later, around, I would say, 1990, 1995, they were able to fabricate particle where the confinement is the three direction of space that we call quantum box, where the particle were in fact just caught in a box, or quantum dots. So my study was actually not only investigate the way electron or other particle like holes, we call holes also, moved into this quantum structure like this, and how light interact with this kind of quantum confined particle.
So what are the quantum dots? Could you talk a little bit more about that?
Yeah, a quantum dot, as I mentioned, is a quantum box. So that means that this is a small structure, also a dimension of the order of a few nanometers. So where the particles like electron are completely confined, so they're in a box, and so they exhibit quantum state like, for example, an atom, but they actually are also called from artificial atom, because you have a way to, in fact, tailor the potential of the force that actually act on the electron, and then you can realize this kind of artificial atom where the electron can jump from one state to the other and things like this. So with the quantum box fair, actually very interesting and fascinating structure because they can contain just a few electrons. Okay, even 1, 2, 3, 4, and things like this. And so this opened in the, I would say, mid-90s, last centuries, a field which is called single electronics, when we can actually see the presence of a single electron in a box, or also single, 2 or 3, but just a few number of electrons. This is actually was the idea was at that time the possibility to realize memory with only one electron and do all the function like this. Okay, so aside from this, because you have electron, they can also exhibit single spin of the electron. The spin is the degree of motion of the electron upon himself. Okay, this is a rotation of, okay, and you have two state up or down. And so there was a possibility with the dot like this to manipulate the spin of the electron and actually give rise to quantum computing.
So, what are the spin effects? Could you describe the spin effects in nanostructures?
Yeah, as I mentioned, so you can actually, because you were able to isolate one or just a few electrons, they interact a certain way. And so this, they not only because the 3 degrees of freedom is now represented by quantum number, okay, like the quantum number in atomic in the atoms, but in addition to that, there was also a fourth quantum number, which is a spin. And the spin can actually have, in quantum mechanics, everything is, well, the dynamic and the property of the particle are represented by integer number. Okay, except for the spin, this is half an integer, and half an integer number, so they can have only 2 number plus 1/2 and minus 1/2. So the plus 1/2 is actually a rotation like this, okay, which actually gives you a motion vertically up, and the minus 1/2 is just a motion like this down. This is, of course, a classical representation of the spin, but of course, this is in quantum mechanics is much more complicated than that. And so because the spin is a pure quantum, is just a quantum entity, the ability that we have, in fact, to make electron interact with each other, they not only have what they call a repulsion among them because they are negatively charged particles, okay? But when they interact in an atom, for example, the spin is important, okay? Because they have what is called an interaction which is purely quantum, which doesn't have any kind of equivalent in classical physics, like at our level here, which is the exchange interaction. And when two spin are parallel, okay, they actually more or less repel each other, but when they are like anti-parallel, there was some kind of an attraction. And so we could see this in quantum dot. Before the emergence of this quantum dot, you can only just study this effect in natural atom, for example, of many particles. But with the emergence of this dot, we have the possibility to see how this spin interact, and we can manipulate them. And so one of the ideas, in fact, for quantum computing was to realize what they call quantum gate. Okay, when you have two dots which are interacting, which are coupled, and this would actually, if you want an analogy, this would be, in fact, the artificial representation of a molecule of hydrogen, H2. Okay, but here you have the opportunity to, in fact, control the interaction by an external electrode to make the electron either move away or bring them together and observing the exchange property. So there was actually one of the theorem in quantum computing which actually described the possibility to realize this gate. This gate we call a C-naught gate, which actually the basic element to achieve quantum computing with the spin of the electron. We are not talking about many spins here. We are just talking about two or three electrons. So this was really remarkable.
Mm. Well, I also want to ask you, what do you see as the future of quantum computing?
Well, and I actually, in the turn of the century, I was participating actually with an international team on trying to achieve this kind of system where we could have many gates like you would have actually on a chip, okay, and achieve this kind of quantum system where you can perform quantum computing. Unfortunately, the number of obstacles that you have to overcome with this kind of technology are enormous because everything needs to be very fine-tuned. And although we have the ability to go to, this nanoscale kind of I would say scale, I mean, just dimension. Being able, in fact, to control the size of this dot to the atomic precision was actually very difficult. Okay, and so this, and to repeat that there was a problem of repeatability. Okay, all your dots are not exactly the same, which is different as in nature, for example, uh, because in nature all the atoms of one kind of element are the same, so you can make molecules things like this. But an artificial molecule is actually difficult to repeat exactly the same. So they would always have some kind of what we call detuning between this quantum level, and so it was very. I think that very difficult. I think that the last achievement that I heard of was actually the ability to make six of this gate together. Six of this. Okay, although in quantum computing we don't need much, we don't need many, but six is still a little bit low for just doing quantum computing. But this is not the only what we call scenario to achieve um, quantum computing. You can do quantum computing with spin. You can do quantum computing with actually cold ion, which is uh, a scenario which is actually um, investigated at the physics department here in Illinois, or optically, instead of what we say entangling. You need to actually entangle by the particle. You entangle photon light. And so I don't think that the enthusiasm that emerged at the turn of the century about quantum computing now is still the same. It's a little bit falling down, but it's slowly starting to emerge. I would prefer to talk about quantum information processing than quantum computing, okay, which is a much broader field where you process information quantumly, for example, to get information from one side of the Earth to the other one, or one side of the country to the other one by quantum means. So it's a difficult process because the problem is that the way the world behave at the nanoscale level, quantum level, is different from the way the nature operate in our level. Okay, and so this transition. Okay, that we have to conserve the quantum nature of particle, and at our level here, macroscopic level, say there was always some issue with that, and so this is very difficult. So this has been now 25 years since um, we started this with different program, and it's still painful. But some of the thing will be achieved, I think, but it will take some times.
Yeah. Well, I also wanted to ask you about bio-nano electronics. Can you describe what are bio-nano electronics?
Yeah. So at the same time as I started to investigate this problem of the uh, coupling between two single electron in quantum dots and entanglement, I also got interested in, the ability to merge, in fact, the engineering of biosystem with the inorganic system, or semiconductor. Why? Because at the turn of century, technology allows us, in fact, to control and manipulate solid state material like silicon at a scale which is comparable to the scale of the biological system, like DNA, for example. Okay, so we were able to make structure which are just a few atoms long, and which is in fact what we have in biosystem. And so, so this bio-nanoelectronics, there was also other kind of discipline, but bio-nanoelectronics is actually a discipline that investigates this interaction between the living system and the inorganic system, or the system, for example, semiconductor like silicon, where actually electronics and biology interact at the nanoscale level. That's it.
And what can we use these for, and both now and in the future, do you think?
Well, there was two ways, of course. One of the first idea that we pioneered here at Illinois is, in fact, to realize very thin layers of semiconductors, okay, to mimic the behavior of human cell membrane. You know that human cells are surrounded by a membrane. And so in this membrane, there was a lot of biochemical element that react and things like this. And so, and they interact with the outside world through nano channels, so very small channel, because they are basking in our salted water. So you know that the human body is actually made 75% of water, salted water. And so this cell are actually basking there, just moving around and things like that. And so and they exchange information or through the membrane, through this nanochannel or nanopore, as we call it. Okay, so by exchanging either ions, okay, so the salt is in fact made of two elements, potassium and chlorine, okay, which is sodium or sodium chlorine. Okay, and so we have sodium ion passing through, and so they to actually keep a balance between them. And the idea emerged a little bit before the turn of the century by researcher at Harvard University to use this nanopore to thread DNA and to be able to sequence DNA, which was in fact an important issue in biomedicine, okay, to actually be able to reveal the human genome. Okay, so the DNA is actually the molecule of life, which is made of an helix of what we call a backbone, okay, an helix of two strands, okay, on which is attached what we call bases, okay, and so they actually tied by base pair, and there are actually four base actually, four base in nature, okay, and so two of them tied together and the two other tied together, and so this is a succession of base along the DNA, which actually consists of 3.5 billions of base pair. You imagine the amount of information which is there. And the succession of this base pair, we call the sequence, is actually proper to each individual. This is actually our genetic heritage, okay, that we got from our parents. Okay, and when two cell, female and male, just merged, it was the strand actually merged and constitute this sequence there. And so this is very important because all the information about your biology and your medicine is stored into this DNA. So if you manage to actually decipher this or just find the sequence of this base pair, you have a lot of information about, you know, especially your health and your heritage, where you come from and things like this. Okay, and the future of your the future of your life. So before trying to decipher this cost a lot of money, costed a lot of money, enormous means big labs and things like this, because trying to decipher this kind of 3.5 or 3 billions of base is actually a big issue. So so the idea was actually to thread I come back to my nanopore, the idea to thread the pore, the DNA to the pore was actually such that in addition to going to the pore, the ion also goes through the pore. So you have an electrical current going to the pore because the ion is charge, okay, positive charge, okay. For example, sodium carry a positive charge. When you go to the pore, this actually achieve a current. And so if the pore is open, then you have a constant current. But every time that you thread a DNA to the pore, it blocks the current, okay. And depending upon the base that is attached in the pore at the moment you measure it, you block the current a certain way. So the current, they say the current that you reflect, it should be made of step like this, okay? And the height of the step should actually determine your base. So by threading this, if you can read this, the signal giving, you have actually the genome. Okay, so they come back to my researcher at Harvard University. Okay, they would do this with biological pores. That means that they would take human cell and in the pore, they would thread this. But then we realized that now with nanotechnology, the semiconductor nanotechnology, solid state nanotechnology, we can achieve dimension, thickness of semiconductor material, which are similar to the thickness of the membrane, biomembrane, okay? In addition to that, we have instrument also which allows us to dig holes into this membrane, which are the size of the pore, the diameter of the pore. So we realize that actually if now we're using solid state pore to thread the DNA, okay, and look at the same way, but we realize something else, that now we are dealing with semiconductor technology, which has been actually extremely mature and developed. So we can use, in fact, the property of the semiconductor membrane to read the DNA to another way, not only by blocking the ionic current, but also if now we are flowing a current, along the membrane, okay, with the pore, the current will be scattered by the base, and this would be another way to read it. And so this is actually what some of the proposal we made, okay, with other people, but we did it a certain way to achieve this kind of reading. But we can do this with DNA, but we can do it also with protein. We could also just read the protein. We can do the reading of large numbers of biomolecule, okay? In addition, so in addition to that, on the DNA itself, okay, sometimes you have breakage. That means that the DNA breaks. One of the strands of DNA break, and so you can actually, sometimes it's repair itself, sometimes not, okay? And so you can actually, hopefully, find where this break occur in the DNA, okay? If you have too many of this breakage of the DNA, then this is a problem because it becomes lethal for the individual. The other way, there are actual molecules that attach to DNA, like protein, we call this or just other things like methylation, and this kind of molecule don't affect actually the genome, but actually can affect the physiology of the individual, and so create cancer, for example. We can also try to measure this. So so this is all kind of stuff that you can do with a nanopore. So in some way, the semiconductor nanotechnology, which is highly sophisticated, okay, and can in fact, I would say, help support the analysis and of biomedicine. But in addition to that, we can turn the problem around, and so we can actually store information in the DNA because we have actually something like billions of base pair there. You can store the information there, let it rest, and you can. So in that sense, we can actually store information and use this as a big data storage that we can read with semiconductor technology. So this is actually the two aspects of the use of bio-nanoelectronic with nanopore technologies that I'm investigating now since 25 years.
Yeah. Well, so what do you see as the future of nanotechnology?
I don't think that we can already talk about not the future, but I mean the achievement, because we have already achieved a lot with nanotechnology. And I think this is going to continue in many aspects of life. Actually, what we are doing right now, we are using nanotechnology because, you know, the chips that are in computers and things like this are actually fabricated with nanotechnology. The communication processes so done with element fabricated with using nanotechnology in car, everywhere, nanotechnology. The ability, in fact, to use and to use this technology at the almost atomic scale. Nanotechnology is another 10 above the atom size. An atom size is actually 1 angstrom. A nanometer is 10 times an angstrom, let's say 10 times an angstrom. So now we are able to use a technology which is 10 or the order of 10 times higher than an atom. So we are really manipulating, you know, the matter and well, in not only solid state matter, but also soft matter like biology and things like this at the atomic and molecular level. Individually. This is important thing, individually.
Hmm. Well, you mentioned some of the potential impacts to society and our daily lives, but could you talk a little bit more about how this will impact our daily lives and society?
This, I tell you, this, everybody is using cell phone right now,
Yeah.
right? No, and AI, people are talking about AI. AI, the fact that AI is possible is simply because you can store information on a chip, which is 1 centimeter square. And on these chips, you have billions of logic device like transistor that operates. So AI, the people are talking about, I mean, heard Bill Gates talking about now that some of the doctor will be replaced by AI biodiagnostic will be replaced. This is done possible because nanotechnology, because our ability to function, to make material and system that function, okay, simple function at the nanoscale level, okay. That's the ability. So it's just enormous. Everybody without knowing it, everybody is using nanotechnology.
Hmm.
Not only in America, not only in Europe, not only but you can go everywhere in the world, you know, can go to Africa. People are using it. So this is everywhere, all continent.
Yeah. Well, Jean-Pierre, thank you so much for taking the time to talk about your research and your insights, and I hope we can continue the conversation down the road.
Okay. Thank you very much. I hope that that was helpful.